Hi there, my name is David Gardner, and this is my lab report for Lab 2, line charges. Now, the purpose of this lab is to recalculate the electric force of the point charge model from Lab 1 using the line charge model. And just as a preamble, the results I found were that my point charge was 1.027 times 10 to the 8th, 10 to the negative 8th coulombs, and my line charge was 2.73 times 10 to the 8th coulombs as well. So before we get into things, there are two important concepts that we have to cover, as with the last lab. The first being Newton's second law. So Newton's second law describes the relationship between acceleration and force, which we can use to find the force of gravity. And Coulomb's law describes the interaction between two charged particles, which in this case would be our tapes, and the distance between them, the r, the r will be represented as the distance between them. As you can see here, there was a lot of data on Lab 1, and so I want to refresh you guys a little bit. So in Lab 1, we had two U-tapes that we created, and we measured the displacement when we placed one U-tape next to another U-tape. Now, using these initial values, this length, this width, and this mass that we found, we were able to eventually calculate the force of gravity on the tape and the charge on each tape, with some assumptions, of course. And you can see here the point charge model with the system being described as the red circle, and the surroundings, in this case being the tape, being described as the blue tape, or as the blue sphere. And you can see our calculations down here that are mostly miscellaneous, but also some of them are important, like the charge, for instance. Now in Lab 2, we also had to calculate that force of gravity, which we found to be 2.62 times 10 to the negative 3rd newtons. And from once we had that force of gravity, we could say equal to the force opposing gravity, or the electric force in this case, which we found, would also have the same value, since they would be forces in equal but opposite directions. And now here we use a different calculation for the charge of an atom, or the charge of we're using a different calculation to discover the charge, since in our new model we're representing the charge as a rod or a collection of points, basically. At each point, the charge is going to be described by this formula here instead of the Coulomb's law. Instead of like the generic Coulomb's law formula, we instead have a derived counterpart to it, and that value ends up being equal to 2.73 times 10 to the negative 8th coulombs, where L is the length of the tape at 10.5 inches or 2.667 meters, and R being 3/4 an inch or 0.1905 meters. So after making those calculations, we could start to begin to build our model. And so I start off with the model constants and functions. Now, in our model constants, we had 1 over 4 pi epsilon squared, represented by 9 times 10 to the ninth, and the gravitational constant of 9.81. I also plugged in our mass, the mass of our tape, in kilograms instead of grams, and the estimated net charge on one tape using the prior formula described here. And I also inputted our length and our distance between the two point charges. And for our functions, we had this electric field function, which took it took in a charged particle in observation location. It subtracted the observation location from the particle charge in order to get our r vector, and then we multiply that by our k constant, 1 over pi epsilon squared, or no, 1 over pi epsilon 0, sorry, and the charged particle's charge over the magnitude squared and in the direction, or the r hat of r, and then we return that e vector. And then we have this line charge function, which basically it would take a line of uniform points and basically create the dl of our or it would create the dl's of our line, basically. So it would take our line, divide it by n lengths, and create point charges at every length, basically, which is our line charge representation. Now, some assumptions I made were that the charge of each tape was distributed evenly, basically. So obviously there'd be small micro differences in how the charge is distributed on the tape, but that's not something I account for in this model. I also made the same assumption as Lab 1 that each U-tape had the same amount of charge. And I also had the assumption that air resistance and friction are negligible, which is not always the case, even if they have a small impact, it would be hard to quantify in this model. And some potential sources of error by that logic are the would-be excessive contact with the tape, leading to reduced charge, the precision of our measurements, as we were using inches instead of meters, and the length of our tape because we used a 26-meter tape instead of a 20-meter tape, which may have caused different values. And as for the discussion, um, comparing the charges we got, obviously we had 1.27 times 10 to the 8th for our point charge and 2.73 times 10 to the 8th for our line charge. And so the reason why I think these estimates differ so much is because with the line charge, we're treating the entire tape as a series of point charges, and so therefore there are more calculations going across the whole tape. And when you sum those up, you're going to get a larger value than simplifying it as a point charge, where as a point charge, you lose a lot of length represent like it's hard to represent the length, if that makes sense, that your line charge can capture, you know? And so if I had to choose a value to be closer to the real thing, I would assume the line charge just because we have it's more in depth and it's more accurate to the shape of the charge. Yeah, it's more accurate to the shape of the charge distribution. Um, and so yeah, that would be my take is the line charge.